So a very good afternoon to all. So welcome to the afternoon session. So here we have Dr. Sreejith. I would like to give a small introduction about Sreejith sir before we start. So Dr. Sreejith graduated in EEE from Noorul Islam College of Engineering. He obtained his master's in Power Electronics and Drive from MEPCO Engineering College, Sivagasi. He did his full-time doctorate at NIT Trichy on the area Power Electronics Applications to Power System. Presently, he is working as the assistant professor in the Department of EEE at NIT Silchar, Assam. Before joining NIT, he worked as associate professor in the Department of Energy and Power Electronics in VIT Vellore. Having 16 plus years of teaching and research experience, he has published more than 50 papers in referred international journals like IEEE, Elsevier, Springer, and a lot of international conferences. He is a reviewer in IEEE, IET, Elsevier, Taylor and Francis, Springer, and a lot of other journals. He is also serving as a member of editorial board in a few journals. He has given a number of lectures and hands-on training in power electronics, power systems, drives, facts in HVDC, smart grid. He is also a member of BYS, Board of Studies in various institutions, and very glad having him here. His research areas include power electronics, power system, renewable energy sources, drives, smart grid, optimization techniques, facts, HVDC, and electric vehicles. Sir, we feel very elated to have you here with us for this final session of this 2 weeks FDP. And he is here with us to give more idea on recent optimization techniques used to solve electrical engineering problems. Now, I request Dr. Sreejith to take over the session. Thank you.
Thank you, sir. Let me share the screen first.
Yes, please, sir.
Is it visible?
Sir, yes, sir, it is visible, sir.
Okay. Yeah, very good afternoon to one and all present here. It's my pleasure to meet you all in this online platform. First of all, let me thank the coordinators for inviting me for this FDP. And thank you, sir, for your wonderful introduction. So for the past 2 weeks, you are attending a lot of nice lectures on machine learning, fuzzy systems. I've seen a few on renewable energy systems. So a lot of things. I hope you have enjoyed all the sessions. So today the title which is given to me is recent optimization techniques in electrical engineering. There are a lot of techniques used in electrical engineering application, but let me stick on only one. That is an ant colony optimization technique. There are a lot of things, but for example, I'm taking this. Okay. So if we see optimization, okay, so most of us are using that, right? The thing is that it's very tough to separate optimization from research. If you see the number of scholars working, more than 60% of the people will be using at least one optimization technique. Okay. Or if you see the number of papers published, more than 50% of paper you can see they'll be using a lot of optimization technique. Okay. And if you specifically see with respect to electrical engineering, okay, I'm just talking about electrical engineering. We have a lot of areas, right? Power electronics is there, power system is there, control is there, a lot of areas are there. If you are just taking power system, okay, if you have a lot of problems, right? If you go for load flow is there, economic load dispatch, optimal power flow is there, unit commitment, security consent, a lot of problems are there, right? So you can see most of the problems people are using optimization techniques. Apart from this one, location of fax devices, location of capacitors. So everywhere optimization technique is used. And not only on that, if you go for control system, if you have a controller, how to tune the parameters, that's also a good example for optimization. So everywhere you can see optimization. Okay. So anyway, but I don't want to explain what is an optimization and all, because for the past 10 days you are hearing the same thing. Okay, but in general, if you go for optimization, normally I will be doing optimization to get a better result, right? Either it can be minimization or it can be maximization. That depends upon the application. If you are doing something with respect to the profit or something, it will be maximization because I need to maximize the profit. Whereas if you want to doing something with respect to the transmission line or the generation cost, then it will be doing minimization. So maximization or minimization depends on the application. Okay. And when you're going for optimization, you'll be having some objective function which has to be either minimized or maximized, and which are subjected to a lot of constraints. If I'm taking an economic load dispatch, then we'll be having the cost function as objective. Then we'll be having a lot of constraints, right? That means the total power generated should be equal to the load plus demand. That will be one constraint. Then the real power generation should be within the maximum and minimum limit of the generator. Reactive power should be within this limit. Then sometimes you'll take the line flow also. Transmission line is having the maximum limit. So all such constraints will be there. So in order to get a better value, okay, subjected to all these constraints, we'll go for optimization. Okay, and let me give the outline of the presentation. We'll be starting with uncolony optimization. That means what is actually uncolony, what is the history behind this one, okay, what is actually the inspiration, because all these techniques now with respect to some process or something only they'll be creating all these. Okay, so what is the inspiration behind uncolony optimization? We will see. What are the parameters, because whatever optimization you take, at least one or two parameters will be there to tune it, right? So we'll see what are the parameters in ACO and colony. Then we'll see what is the exact explanation of colony optimization. And finally, if time permits, I'll just tell you the mathematical model. But it's a generalized example, not with respect to power electronics or power system, just with respect to generalized expressions. I'll tell you how to model this AC. Okay. So these are the things which we are going to see for the next 1.5 hours. So when you go for optimization technique, we will be calling certain things as heuristic algorithm, certain things we will be calling it as meta-heuristic algorithm, then we will call it as swarm intelligence. Lots of classifications are there. Okay, but when you're going for this one, what is the uncolony optimization? Mostly it will be coming under meta-heuristic algorithm. So if you take heuristic algorithm, I'll just go through the slides introduction. When it comes to uncolony, then I'll start explaining. Okay, so if you go to heuristic algorithm, the thing which we have is it is problem dependent. Okay, that means the algorithm depends upon the problem. Clear? And we need to know about the exact problem before writing the algorithm. Whereas when you go for meta heuristic, it's not the case. Okay, it's problem independent. We don't want to know what is the problem. Just you need to write the algorithm. So that is the biggest thing. I'll just admit about meta-heuristic, problem-independent algorithms. So I can use this problem for economic load dispatch. I can use the same algorithm. Sorry, I can use the algorithm to go for optimal power flow. I can use the algorithm to locate the fax devices. I can use the same algorithm to reduce the harmonics, because when you go for power electronics, we have something called as a selective harmonic elimination technique. So I can use the same optimization there also. So this is problem independent. Okay, and we don't want to know exactly about the problem. Okay, so for writing the code, for example, see when you go for a MathWorks file exchange and all, when you are downloading the codes, you can see certain codes are written with respect to that algorithm. Okay, that means with respect to that problem. So it will work for that problem, but if you try to edit it for our problem, it won't work. So it's actually problem dependent. They wrote exactly for that. But there are certain things, okay, so code, optimization code will be running in one file, and for example, our code will be in another file. So it is problem independent. So whichever you want, you can incorporate inside that. Okay, so that is the advantage of having meta-heuristic algorithm. Okay, and mostly these will be coming under swarm intelligence. Okay, it is actually a natural phenomenon, or whatever happens in the nature, the same behavior is converted into mathematical expressions. So just for example, let me tell. See, let me take the human beings itself. Okay, assume that you are driving the vehicle, some vehicle. Assume that I have just a level crossing is there. Okay, I have a level crossing. That is a train is crossing there. Okay, so when you are going through a vehicle, will be stopped in this end, right? What are vehicles which are coming at that from that side, they will be stopped at that end. But actually what we need to do in we need to stand just mostly to the left extreme, such that the vehicle which are coming from that side will move to the right, and we can also go. That is a normal rule we have. But generally what we used to do when we are just stopping in the level crossing, we will be just making a huge crowd there, right? On that side also the same huge crowd will be there. But when the gates are open, we won't be able to go there and they won't be able to come there, because a huge crowd is there on both the sides, right? Where the same thing if I'm taking other organisms, for example, if I'm taking bird, okay, if you see birds when they are flying, okay, you can see they'll be maintaining equal distance between each and every one, okay, and they'll be flying in the same velocity. Okay, that is actually the inspiration for PSO, particle sum optimization, because with respect to that bird only PSO has been created. You can see that they'll be flying in the same velocity and maintaining the same distance, but there is no rule written for that. Right, that is the inspiration which we are getting from them. Or if I'm taking ants, okay, you might have seen ants in a home, right? It's very tough to live without ants. Everywhere it will be there. So if I'm seeing ants, initially if you see ant, some food source is there, means they'll move randomly here and there. But after some time, you can see within 1 or 2 minutes they'll be going the straight line, right? If you disturb them also, within a minute again they'll follow the same straight line. Okay. So these are all the inspirations which we get it from those organisms, from those creatures, and we'll be creating these algorithms. Okay, so they are swam. Okay, that means a natural phenomena. Those things that happen naturally, that we are adapting and we are converting it into algorithm. Okay, ants are there. Birds will be flying. Everything has certain rules within them, right? They are following the rules and they'll be using the same set of things. We'll be converting it into mathematical equations and we are using it for our problem. Okay, so these are certain things. Okay, right. And you can see n number of meta-heuristic algorithms. Okay, I just taken detail from internet. If you see meta-heuristic algorithm, you have number of algorithms. Okay, these are some examples. Okay, I might have missing something in between. Don't worry for such things. Okay, see for example, if I'm taking ant colony, it resembles the behavior of ant. Particle sum optimization, it resembles actually how birds are flying. Harmony search means how a musician is creating a better harmony, better music. So that is converted into equation as harmony search. Artificial bee colony, how the honeybees are finding the food source, that is their foraging behavior. With respect to that, they'll create an algorithm that is artificial artificial bee colony, ABC. Okay. So with respect to this, you can see n number of meta-heuristic algorithms are there. Up to 2021, like recently they have something called as jellyfish search. So these are a lot of meta-heuristic algorithms we have. And normally as a research paper, what we used to do, we used to run one algorithm, we'll get a result, we'll compare the result with other algorithms, we will tell you that's the best. Like this only things are going. Okay. Now let's move on to ant colony optimization. Okay. So if you see ant colony optimization, that was first proposed by M. Dorigo in the year 1992. He was actually doing his PhD. In the PhD thesis, he proposed this algorithm. Okay, but initially, this ant colony optimization is called as ant systems. Okay, ant systems. But now it is actually called an ant colony optimization (ACO). Initially, it was ant systems. Now it is ACO, ant colony optimization. But there are a lot of new categories for ACO. ACO real is there. ACO is there. Okay. Then you have ACO real is there. Then you have TACO, Turing and colony optimization is there. Then NACO, a lot of modification. That is the first one is ant systems. Then and colony optimization. Then some modification. Then it is Turing and colony. Then some modifications will be done. That will be nodal and colony. Like these things are going. But the basic one is and colony optimization. Okay. One is such a probabilistic technique. I'll tell you how we'll be calculating probability. And if I'm taking an colony optimization, see when you go for optimization techniques, we have two kinds, right? One is you have a discrete optimization technique and you have continuous optimization. I mean, continuous optimization. Both are there. Discrete is there and continuous is there. Okay. But if you see the literatures, okay, so ACO is mostly applicable for discrete optimization. Actually, it is done for traveling salesmen. That is the first one. Then actually this is used only for, I mean, used for this. Okay. continuous optimization technique also, you can use ACO. I have used it, but the thing is that you won't get a better result always. So mostly it is preferred for discrete. You can use it for continuous also. Okay, and for continuous, they have developed another ACO that is called as ACO real. This is suffix. Okay, so that is the thing which we have with and colony. So mostly applicable for discrete. For continuous also you can use, but we can't expect the better result always. Okay, but ACOR is there that can be used for continuous. That is specifically done for continuous optimization function. And initially, this ACO, when it is actually presented by that is Dorigo, it has been used only for traveling salesman problem. You know, right? Whenever you go for an optimization technique, most of the people, they will explain with respect to the traveling salesman problem, right? You want to find the shortest route. Okay. So this was also implemented for traveling traveling salesman problem. But by seeing the better performance of this algorithm, this has been extended to a lot of other applications. Okay, that's why we are using it for lots and lots of applications nowadays. Okay, and this actually depends on, this is actually based on how the ants are finding the food source. Okay, how the ants, they are finding the food source. That is actually the technique which is used in ant colony optimization. Okay, see, the thing is that it depends on, anyway, I'll come to next slide and I'll tell you. Okay. The main inspiration behind and colony optimization is stigmergy. This is very important. The main inspiration behind and colony optimization is stigmergy. Stigmergy means it's an indirect communication. I'll just tell you with one glance side. See, for example, I'm sitting in the extreme northeast, Silchar. Okay, my hometown is in Kanyakumari. If you want to go to my hometown, so I have booked flights and all, that's all. But I'll just make a call to my parents and I'll inform that I'm coming. Right? That's a normal procedure I used to do. Right? Worst case, I can put a SMS or I can put it in WhatsApp. Very rarely people will mail also. But whatever it is, this is actually direct communication, right? I'm calling them and telling that I'm coming there. That is the information, right? Either to call or by WhatsApp or by mail, everything it is directly communicated that I'm coming. So that is one type of communication. Another one is indirect communication. Indirect communication means they won't tell this directly, but by seeing the environment condition, people can understand what is happening. So the best example I can tell you is that you might have seen honeybees. Okay. See, since I'm dealing with swarm intelligence, I need to explain everything with respect to those organisms only. Okay. You might have seen honeybees, right? Everywhere it will be there. Okay. Assume that I have a hive here. Okay. Sorry, I have a hive here where I have a lot of honeybees flying here. Okay. See, if you want to know, if you try to know the life of all these, now they're really interesting. Okay. If you see ant, how they are finding food, that is interesting. If you see the life of a honeybee, it's really interesting. Okay, because it's nice to know all such things. Okay, let me explain you how honeybee finds what is the stigma in honeybee. Okay, now I have a hive. I have a lot of honeybees flying there. Okay, I have some flower here. Okay, so one honeybee came here and it has identified the flower which is having the honey. That's all. Okay, honeybees will fly here and there, and one honeybee has came here and they have identified that flower honey is there. Okay, but if you see practically within a fraction of minutes, all honeybees will go there. They'll go there and they'll take honey. Okay, that is what happening. But how this honeybee is informing other honeybees that I have found out a food source, that is important. Okay, the first honeybee has found a food source. Okay, but within a short period of time, all the honeybees will go there and they'll take the honey. But how the first honeybee informed others? That's the thing. Because no mobile, no cellular network, nothing, right? They're just creatures, right? So you don't directly call a honeybee and tell I have found a food source. That is also not there. But it will dance. That dance is called as waggle dance. If you go deep into the life of a honeybee, you can see all such things. Waggle dance. Okay. So this honeybee, when it is finding a food source, okay, it will make a dance which is called as waggle dance. So the way in which it is dancing indicate how far the food source is from the hive. Okay, that means if the distance is example 40 meter, okay, so how it is dancing will indicate that it is 40 meters. So for 30 meter the dance will be different, for 20 meter the dance will be different, and for 50 meter the dance will be different. Honeybees can understand that. So the way in which it is dancing will tell that how much distance the food source is from the hive. Okay, so the other honeybees can understand by seeing the dance. It can understand he has found out a food source within this distance. That is one thing. And the second one is that, okay, this dance also indicate what is the angle at which the food source is there. Okay, this is a hive, it is in some angle, some theta. This is angle, right? So this food source is in, because distance is 40 meter, okay. But if you take a circle, they can go anywhere 40 meters, right? 40 meter is here also, 40 meter will be here also, anywhere it can go 40 meters, right? So the thing is that because the vibration of the dance tell how much distance it is. But where exactly the food source is, that is given by that angle. So the dance will indicate that how much distance the food source is and in which angle it is there. Okay, you can see for each and every angle the dance is different, and for each and every distance the dance is different. This is the best example of stigmergy. That means communicating indirectly by seeing the dance, that is the environment. Other bees can understand where the food source is, how long it is, and what is the angle at which it is there. Okay, so this is stigmergy. Okay, and just think of ants. Okay, so stigmergy is a indirect communication, the interaction with the environment. This hope you can understand what is stigmergy. It's an indirect communication in via interaction with the environment. So the dance is there. With respect to the dance only, bees will understand how things are happening. Okay, and okay, that is for the bees. Yeah, well, let me see ants, because it's ACO, right? How ants are communicating. I have an ant. It has found out if ants are blind, right? Ants are mostly blind. Okay, so they can't see, right? But you can see, one ant has found out a food source. After a short period of time, all ants will follow the same path. Even though they are blind, they are following the same path. So how this ant is communicating, that is actually the stigma. Okay, that is the indirect communication they have. That is the beauty of these techniques. Okay, so stigma means it's indirect communication. Okay. Right. Now, before going into, so hope you understood what is stigma, right? Indirect communication. But before going into the colony optimization, let me tell you one analogy which will tell you what exactly ACO is or how it is working. Okay. Right. Consider that, see, when you are telling an analogy, mostly it will be past, very past story. Okay. So it's 227. Okay, so assume that I have a source and destination. Assume that this is a village, okay, in which a lot of people are living. It's very long back, okay, and this is a destination where they are going to take water. Okay, they are going to take water. Okay, so this was a very long back. So at that time there was no mobile, there is no telephone, there is no communication device, there is no vehicles, nothing. They need to walk and they need to take water. From this diagram, you can understand that two paths are there. One is path 1, other one is path 2. Path 1 is the shortest path. That also you can see from this diagram. But when they are moving here and there, is very tough to understand. Someone will walk slower, someone will walk faster. Okay, so they are not able to identify which is the shortest path. Okay, so one day, two people, okay, they try to analyze how to find out the shortest path. Okay, so P1 is person 1 and P2 is person 2. Okay, so what they decided is that they are going to take water, right? So what they decided is that while going from the source, okay, they'll pour water in the path and they'll go there. Okay, and while returning also they'll be pouring water in the path when they are returning. That's the decision. Okay, they are not going to communicate directly. They are not going to call and tell, I'm here, you are there, this is distance. They are not going to do anything like this. Okay, simply what they're going to do is that they'll just pour water in the path where they are going. In the same, when they are returning back also, whatever path it is, they'll be pouring water while they are returning. That is the thing. Okay, now let me start this analogy. Okay, so it will be a bit late because for each one I need to take different colors. So now person 1, he has moved it. Okay, he is pouring water and he is going path and he has reached this destination. Okay, so now person 1, he has moved in this green color path and he has moved the reached the destination, and you can see that line indicates that he has poured water. Okay, but you can see path 2 is bit longer. Okay, assume that path 2 is bit longer. Okay, so when the person 1 has reached the destination, person 2 has reached at least some 70% of that path. Okay, person 2 has reached just 70% of that path. Okay, now this is okay. Again in the second round, okay, the first person, he went there. Okay, he took water and he was returning. Okay, he took water and he is returning now. Okay, so he is returning through the same path. Okay. So while returning also, he has poured water and he came back. Okay. So this one side is over. Now the second person, what he is doing is that he has reached there. Okay, he took water, and while he is returning, here only he'll be deciding this. Okay, can see he is having one path here and he is having another path here. But you can see this path has only one line. That means a little amount of water he has poured. Whereas you can see the path 2, he came, he poured water while coming and he poured water while going also. The amount of water which is present in path 1 is more than the amount of water which is present in path 2. See, assume that they are pouring the same quantity of water. Okay, if someone is pouring more, then the case will be different. Okay, assume that they are pouring same amount of water in the path. When the second person is returning and he is reaching the junction, if he is seeing both the path, he can understand that in path 1 there is more wet because the first person came and went. Both the times he has poured water. Evaporation will be on both the sides. If it is same, then no issue. Okay, so he can understand that in path 1, it is more wet because the first person has came and went. So he can understand that this is the shortest path because shortest path means he can come soon and go soon, right? He can come soon and he has went off. So that's why two ways there. One way while coming he has poured water and while returning also he has poured water. So wetness is more in path 1 compared to path 2. So the second person also obviously will take the same path because wetness is more. It indicates that the path is short. Okay, so this is how he has identified the path, the shortest path. Okay, so this is one analogy where we can identify the shortest path. Okay, so we are all human beings, right? We'll have another question also. What happens if second person is taking his actual path? Okay, so let me see here. He has came here. Okay, right. One second. This person came and he has went. So two lines are there. And but you know human beings, right? They have some intuition. Okay, I came to path 2 only. Let me go to path 2 itself, right? Again, if the second person he is taking the same path, okay, he's taking the longest path again. But what will happen is that before this person is returning to the source, okay, this person, right, the first person, he would have completed one more round. Okay, because that is the shortest path. So again, when the second person is coming here, he can understand that he has 4 here and he has only 2 here. So now also you can understand that the path 1 is short. Okay, so this is how it. This is actually stigmarchy. That means indirect communication. There is no direct communication between them. Just seeing the wetness of the path, they can understand that this path is shorter. This is stigmarchy, and this is an analogy which we are going to use in ant colony optimization. Hope you can understand this. Okay. So now let me come to the overview of ant colony. So what I was in just an analogy. So now we'll see with respect to ant colony. Okay. So what exactly happens is that ants will navigate from the nest to food source. So ants will be having nest, right? You can see ant nest is there everywhere. Every home it will be there, right? Then it will go for the food source. But keep in mind that ant is blind. Ants are blind. Okay. Once again. Okay, so the chat is open, it seems. If you have any clarification, just you can put it in the chat. I'll just see and reply. Okay, because time is short for us. Okay, and the thing is that, but even though they are blind, they are finding the shortest path, and all ants are moving in that path. So the reason behind this is, whenever an ant is moving in a path, it will secrete one chemical, that is hydrocarbon, which is called as pheromone. Okay, so this is another concept. Okay, that means whenever an ant is moving in a path, it will secrete hydrocarbon, which is called as, that is a volatile hydrocarbon, which is called as pheromone. Okay, pheromone. By sensing this pheromone only, all other ants will be moving. Okay, so each ant will move random. See, just an example, if I'm taking in my home, okay, we can see that you just put some food source somewhere else, somewhere ants are there, some other place. Okay, you can see that all ants will be coming in different directions. Okay, but after some time you can see all ants will move in the same line. That will be the shortest path. You can identify that is the shortest path. Okay, even we don't know what is the shortest path. We just see that they'll find out the shortest path. So initially they'll be moving in random, but finally they'll find the shortest path. Okay, and whenever an ant is moving, it will deposit a chemical which is called as pheromone. Okay, and if more pheromone content is there, then more chance is there for the next ant to follow that path. Okay, if more, and whenever we are solving the problem, we'll always assume that all ants have the capability to deposit same amount of pheromone. Okay, but when number of ants are changing, this pheromone will change. Okay, 2 ants are there means 2 pheromones. 10 ants are there means 10 pheromones. But keep in mind that all ants are secreting only one pheromone. That means if one big ant is secreting more pheromone and small ant is secreting less pheromone, means everything will go off. So whenever we are solving the problem, it is assuming that all the ants are secreting the same quantity of pheromone. Okay. So when more pheromone content is there, there is more chance for the next ant to follow that path. Okay. Now let me just tell you how it is happening. Okay. Then we'll see what is ACO. So consider that I have a nest. Okay. See, one important thing is that, see, if you are understanding the basics of ACO, then it's very easy to write the coding and solve problems. Okay. But if you are simply just seeing only the equations and solving it, it's very tough to understand. Okay. So I'll just take one more analogy. So assume that I have a nest and I have a food source. Okay. There are 2 ants. Okay. One is a red ant, the other one is a blue ant. Okay. One is red, the other one is a blue ant. So now the red ant is coming here. Okay. Sorry, it's a purple ant. Okay. So purple ant is coming here and the red ant is also coming here. Okay. Now the thing is that I have 2 paths, but by seeing the diagram, you can understand both of them are identical, right? The distance is same for both. Okay. The distance is same for both, right? So the probability of choosing, let it be path 1 and it be path 2. The probability of choosing path 1 is 50% and the probability of choosing path 2 is also 50%, because though an initial condition there is no pheromone deposited, nothing is there, right? And can go in any direction in any path. So but still I have 2 paths, so I'm telling the probability is 50-50. Okay, so this is moving in this path, it will reach here, and the next purple ant will move in this path and it will reach here. Okay, right, because they are same distance, so everyone is reaching at the same time. Okay, and now when this ant is returning, okay, since it's same color, I will take this first. When this ant is returning, it can see both the path. The top one path is there and bottom another path is there. Okay, right? Which path it has to choose? You can see the pheromone content is same in the top and bottom path because the distance is the same. So it can either. So the thing is that it can either take the top path or it can take the bottom path. It depends on it because it's just 50-50 chance there. Pheromone content is the same. Okay. Assume that this ant is also taking this path, the same path. Okay. And when this ant is coming, see they are coming at the same time. There is no time lag. Okay, because the distance is the same. It has also the same option. 50 is there and 50 is here. The same pheromone content is there in the top and bottom. Okay, so it also will take the same path. This is one condition. Okay, now we'll let it be. Let me go to the next condition. Now again the same thing is happening. The first ant is having this path and the second ant is having the next path. Yeah, and this ant is returning. Okay, so in the previous one we have seen that this ant has taken the same path, right? Now the thing is that instead of going in the second path, this is 1, this is 2, it has taken the first path, because see both the paths have 50% only, right? Both the paths has 50% probability. It can take any path. In the previous one you have seen it has taken the same path. Now it is taking this path. Okay. Yeah, and the red ant, obviously that is from the same. Okay, same, and it is also taking this path. Okay. Now first round is over. Now let's, when the second round is coming, when they are going to take food again, they can see that in the first part the pheromone content is much more, and the second part the pheromone content is very less. I mean less, right? Compared to the first part, the pheromone content in the second part is less. Okay, so now the probability is actually 50-50 will change to 75 or 75-25. Just an example, it will change to 75-25 because in the first path 3 lines are there, so a lot of pheromones will be there. In the second path only 1 line is there, less pheromone, and pheromones will evaporate. Okay, so now again obviously what will happen is that this ants will take this path only. Okay, and after some time what will happen is that the entire second path will disappear because pheromones will evaporate with respect to time. After some time, entire second path will disappear and all the ants will pass through the first path. Even though the paths are the same distance, after some time it will take only the first path in this one. Okay, clear? This is how they are taking the same path. Okay, right. Now let's see if the distance are different. See, first one, both the paths are having same distance, so let it be. It's not an issue to find which path it is, okay? Because both are the shortest, right? Now let's see another path here with path 1 and path 2. By seeing the path, you can understand path 1 is longer and path 2 is shorter, right? But well, ants are going, they are blind, they don't know what is that, right? So assuming that the first ant, so 2 paths are there, okay? So obviously it is 50-50 probability only. Okay, so first ant is moving in the first path. Okay, and second ant will move in the second path. But you can see the second path is shorter. Second path is shorter. So the second ant will reach very fast. Okay, second path is shorter. Second ant will reach very fast. So when the ant has reached, while returning back, I'm sure that the first ant would have reached up to this one, right? Because the second path is very shorter, so it will come, and so when this person is reaching here, the first one will reach somewhere here only because that is the longest path. So the second ant is coming here and it is seeing here. It has one is this option, another one is this option. But this option there is no pheromone. Okay, because the first ant has reached just 70%. So this path has pheromone. So again he will take the same path. Okay. Now the first person is slowly coming. Okay. And he is going here, again coming back, you'll see that he has one path here and he has one path here, but you can see in the second path there are 2 lines, so more pheromone. In the first path you have only 1 line, less pheromone, so this second person will also take this path. Okay. So after some time what happens, first path will disappear and second path will be taken. This is how ants are finding the shortest path. By seeing the pheromone content, they are taking the shortest path. So the same analogy is used in ant colony optimization. This is how ants are identifying the shortest path. Okay. And with some numericals, let me tell you how this is implemented. This I'll take later. Let me tell you how it is implemented. Okay. Any other questions here? Okay, so this is just an example. Okay, so I have a what is this nest or food source here. Okay, and I have a hive here. Okay, I have a food source in the top and I have a nest. Okay, assume that I have 5 paths. One is the first path. This is a second path. This is a third path. This is a fourth path, and this is another path. Let me number it: 1, 2, 3, 4, 5. So, but by seeing this one, by seeing this diagram, you can understand the third path is shorter, right? By seeing this diagram, you can understand that the third path is shorter and fifth path is longer. Okay. But how ants are identifying? Because see, while going to take a food source, right, we have a graph, so we can see this is shorter and this is longer. But when you go for ants, okay, so they are just going to take food. They don't know which is the shortest and which is the longest path. So what they generally will do is that, I'll just tell you how things are happening. Okay, so first one, assume that I have 50 ants. Okay, I have 50 ants. See, this is all for example, I have 50 ants. Okay, but initially, when they are moving here and there is no pheromone content deposited in any path because all the paths are blank. No one has traveled in that path. I mean ants. Okay, so all the paths are blank and no pheromone content in any of the path. Okay, so the probability of choosing all paths will be the same, right? Because there is no pheromone content. Everything is new. So the probability of choosing all 5 paths are there, right? It's 1 by 5 because our 5 paths are there. So probability of choosing the first path is 1 by 5. Second path is 1 by 5, third path is 1 by 5, and fourth path is also 1 by 5. It can take any path, right? Because they are all new. Okay. So what will happen is that out of 50 ants, 10 ants will flow in this one because it's 1 by 5. 10 ants will move in this one. 10 ants will move in this one. So that means each path will have 10 times ants. That's the first iteration. Normally, when you're going for ant colony optimization, this will happen first. Okay. So each path will have 10 times ants. Because the probability is same. It's just a starting. No one knows how much pheromone in it. There is no pheromone content in the path. So all paths are the same. So everyone will go with respect to that probability. But just it's mathematically telling everything has an equal probability. So 10 ants will move in path 1, 10 in path 2, 10 in path 3, like this it will be happening. Okay. Now what will happen is that when it is moving in each path, okay, so they'll secrete something called as pheromone. Okay, they'll secrete something called as pheromone. Okay. So, and all paths will have pheromone, right? But the thing is that the third path is the shortest path. So they can go faster and they'll come back faster, right? They'll go faster and come back faster. So the pheromone content will be more, right? Because the thing is that if I'm moving in a short path, suddenly I can go there and can return. Okay, so while going also they'll be laying pheromone. While coming also they'll be secreting. 1 second. Let me connect 1 second. Yeah, sorry for the interruption. Am I audible?
Yes, sir.
Okay, okay. Sorry, there was a interruption. That's why I was just want to disconnect it. Okay. So the thing is that so these are the initial things which are happening, right? First iteration. Okay. So but whenever an ant is moving, they lay something. They'll secrete something called as pheromone. Okay. But we can know that from this diagram, you can see that the path 3 is shorter. Okay. So they can suddenly go and come. So the amount of pheromone deposited will be more, right? So the let me put one color that tells you the if thickness is more pheromone. Okay, so path 3 actually more pheromone content is there. Okay, because the thickness is much higher. Okay, and in path 2. And this path, path 5 is a longest path, less pheromone content. Okay, path 5 is the longest path, so less pheromone content. Okay, so now we can identify that path 3 is having the highest pheromone content, and path 5, this side is 5. 5 is having the lowest pheromone content. So now we can understand path 3 is shorter, right? But now when you're going for a mathematical formulation, okay, we will be describing this with respect to some probability. Okay, with respect to some probability only, we'll be describing. And we can understand that whenever the length of the path is more, the pheromone content will be less because it has to travel a lot, and evaporation will be there every time. Always evaporation will be there. But when the longest path means it has to travel more time, it will take more time to travel, so evaporation will be more. Whereas shortest path means suddenly you can go and come back, so more pheromone content will be deposited, evaporation will be as usual. If you take the evaporation is same in both the cases, surely the third path will have more pheromone content deposited. Okay, so in the first iteration, the probability was the same, 1 by 5, 1 by 5, 1 by 5 for all the paths. Okay, but when it comes to the second iteration, the probability will change. With respect to this pheromone content only, we will be calculating the probability. Okay, now the probability will change. So instead of 1 by 5, the probability in the third path will change to 1 by 2, may change to 1 by 2. Okay, that calculation I'll show you once I'm showing the equations. Okay, so instead of having 1 by 5 probability, now the probability in the path is 1 by 2. And initially the path 5 had a probability of 1 by 5. Now it will reduce to, it may reduce to 1 by 8. See, just for reduction I am putting 1 by 8. The value depends upon the calculations. Okay, now we can see the probability of the first path is, third path is 1 by 2, and the probability of taking the fifth path is 1 by 8. So 1 by 2 means, again, if 50 ants are coming, 25 ants will go in path 3, right? Because the probability became 1 by 2. Since it became 1 by 2, that is half. So half of the total will go through path 3. That is, since it is 50, 25 will go through path 3. And it's 1 by 8. So if I take 50 by 8, it will be around 6 ants, right? 6 ants will go through path 5. Now you can see initially all the paths are having same number of ants. Okay, all the path will have to, see, it can be 10 or 9, it depends. Okay, just for calculation I have put 10, 10, 10. So in the third path you can see 10 ants, all the path there are 10 ants. Now after the first iteration we are seeing with respect to the pheromone content. So in the third path now it is 25 ants, and the fifth path now it is just 6 ants. So consider that if 25 ants are going and coming, how the pheromone deposition will be. Okay, the pheromone deposition will be much more. Okay, and in path 5 initially 10 ants were going, so pheromone deposition was very less because of the length. Now only 6 ants, so the pheromone content will be still less and the probability will reduce. Okay, after some time what will happen is that everything will get evaporated and path 5 will disappear. Okay, likewise after some time path 1 will disappear, that is the next largest path, then path 5 will disappear, and after some time what will happen is that I have a food source here and I have a nest here, only third path will remain. That is why you can see practically when you are seeing ants, they are searching for food, they'll go through all possible paths and finally they'll go in only one path, that will be the shortest path. This is how ants are identifying the shortest path, and this is with respect to the foraging behavior of ants. The same thing is converted into mathematical equations and it is used as ant colony optimization. Okay, hope this is clear. Okay, now let me come to the theory. I think rather than going for theory, this analogy will help you out. Okay, now let me tell you what are things we have discussed. The same thing will come here. Okay, thing is that in a series of experiments of colony of ants, normally when they are conducting experiments, okay, so initially there were two paths of unequal length, but finally they will be taking only one path, and which is the shortest path. That's what the people have identified. Even though they have a lot of path, the ants will go only through one path, which is the shortest path. And how this is happening? That's because of the pheromone trail which has been deposited when they are moving in the path like this, leaving in its path the pheromone trail. Okay, and the thing is that how they are the ants are secreting pheromone, that is okay, but how other ants are saying that they can smell that pheromone, and by just they'll get attracted by the pheromone content, then they'll move like that. Same what you have seen for what is that, honeybee. They'll be dancing with respect to the vibration of the dance. They can understand that how much distance and how much angle it is. Same as that, just by seeing the pheromone trail, you can see the density or concentration of the pheromone. They can understand this is the shortest path. Okay, you can see then it's best suited for traveling salesman, right? Because traveling salesman is the shortest path. That's why if the first time this ant colony optimization is applied for traveling salesman problem. Now it's applicable for most of the other problems as well. Okay, and two things are there. You need to understand that whenever their pheromones are secreted, they are volatile. They will evaporate with respect to time. Okay, but if it is not evaporating, means again it will be an issue. So pheromones will evaporate with respect to time. Okay, but we need to make sure that as far as ant colony is concerned, they are blind and there won't be any leader. That's the thing which you can see from the ant colony. Whereas when you go for honeybee, queen bee, a lot of people are there, but this one there is no leader and they are blind. But even though they are no leader and they are blind, by having an excellent foraging property, they are identifying the food source and they are finding the shortest path in that. Okay. So pheromone, okay. So ants lay pheromone trails while traveling, okay. And when more number of ants are going in the path, more pheromone will be there, okay. And so when more pheromone content is there, the ant which is coming at the end first, I mean at the last, they can understand that when more pheromone content is there, he can understand more ants have gone through this path. If more ants have gone through this path, then it's understood that it is the shortest. Okay, so this is how it is being done. Okay, right. So this is just explaining. Okay, now let's come to the. These are all the three things. Okay, so diagrams we have. You can see two paths. Okay, one is long and one is short, but finally it will find the shortest path. I think they had three paths, right? In two paths, but finally they'll understand. This is what ants will do. They'll find the shortest. Same thing, if they're going also, if you put an obstacle, okay, if you put an obstacle, this has one path here and this has one path here. This is path number 1 and this is path 2. But we can understand that path 2 is the longest path and path 1 is the shortest now. Okay, so surely ants will go to the shortest path only. So it depends upon the path, and if you put an obstacle in the middle also, they'll try to adjust in the shortest path. This is what ants will do. Okay. This is what just the same thing in a diagrammatic manner. We have seen a nest and food. Okay, first ant has reached it faster. Second ant has just reached nearly 70% of that path. Okay, and first person is moving, but the second person is still going. Okay, and as more pheromone content is there, this path will be taken. This is what we have seen till now. Okay, and finally, one by one the ants will flow through this path, and finally what will happen is that entire ants will take the same path. This is how ants are finding the food and they are finding the shortest path. The same thing is converted into mathematical equations and we are solving problems by using AC. Now let's go on to the mathematical formulation. How this is see, the things are okay, fine. Ants are okay, good. They are finding the shortest path. Okay, they are traveling. They are secreting pheromone. Okay, a pheromone is deposited. It is evaporating. They are finding the probability. Everything is fine, right? But how it has to be used for an application? Then we need to put all those things in mathematical form. And in mathematical form, the movement of ant in mathematical form, secreting pheromones in mathematical form, right? And when more number of ants are moving, more pheromone will be there. So that has to be put in math equation. Then pheromones will evaporate. Okay, so that has to be converted into equations. Okay, and when a lot of ants are flowing, going in a path, the ant which is coming new, that will also follow the same path. Then how it is done? That has to be done with some probability. Okay, so all such things are converted. What we have seen, this is a real-time example, but we need to write all these things in expressions. We want to convert it into an optimization technique. So briefly, I'll tell you how these ant colony optimization, what you are seeing till now as an example, how it is converted into mathematical. Second, let me have a cup of water and So how this has to be mathematically modeled, I'll just tell you. But I'll just explain in general. When you're applying to your problems, you can modify according to that. Okay. So first one is we are talking about pheromone, right? We need to explain. We need to see what is pheromone. Okay. How to model pheromone? Then pheromone will deposit. Pheromone will evaporate. For everything, we need to write the expressions. Next one is decision making. How we need to decide this path is shorter. See, by seeing the graph, we can see, right? By seeing the graph, we can see the path is shorter. But when you're writing mathematically, how to decide which path is shorter? So all these things are depending on certain probability. Okay. Now let's see how to write this mathematically with equation and example. Okay. So it's three. Let me try to take within the next 30 minutes. Just consider an example where I have a source. This is a source. This is a equation. This example available most of the places. This is a source, okay, and these are the path, okay. These are the path which you have, okay, and this is a destination, okay. We have a lot of paths, okay. So let me take this as A, okay, this is B, and this is C, and this is D. That means if I can go from A to B, this is 15. That's a distance. Assuming that that's a distance. If I want to travel from A to B, that is 15 kilometers, centimeter, whatever it is. If I go through A to D, it is 4. D to B, it is 5. Like this. Okay. So this is a cost or distance I have from the source and the destination. I can choose any path. Okay. Any and can choose any path. So let's see how this how to write the equation for such an example. The same thing you will be writing for your own application. Okay. Right. So first of all, how pheromone content is written in mathematically, that is important. Okay. Because whatever I was saying, everything is working with respect to pheromone, right? So how to put it mathematically, we'll see now. Okay. So this is an expression for pheromone. This is a standard expression for this one. When well, we're going for ACO. So delta tau is always for pheromone. So delta tau gives a pheromone content. Ij is the path. That means from I to J. Okay, so I is the source and J is the destination. So from I to J, it's not source and destination. I is one point and J is another point. From when it is moving from I to J, what is a pheromone content deposited? K is the kth ant. If I have 5 ants, K means K is 1 means first and K means 2 means second and like this. Okay, so delta tau is the amount of pheromone deposited. Ij means when it is moving through path I and J for and K. So it's given by 1 by Lk. 1 by Lk means Lk is a distance. L is a distance. K is a ant. Okay, that means kth ant traveling. Okay, so Lk is a distance traveled by the kth ant when it is moving from I to J. Why is 1 by Lk means we have seen, right? The analog is that the thing is that when the distance is more, amount of pheromone is less, because distance is more means it has to travel long time. Okay, so the pheromones will evaporate. Whereas when distance is short means suddenly it can go and come, so the more amount of pheromones will be deposited. So we can understand that long distance means less pheromone. Short distance means more pheromone. Okay, and we want to find the shortest path, short distance, right? That's why it's 1 by Lk. That means longer distance have less pheromone and shortest distance will have more pheromone. That's why it's 1 by Lk. Okay, and 0 means it is not going through path I and J. It's 0. Hope it's clear. This is how we'll be writing the expression for pheromones. Okay, whatever distance we have, it's the inverse of that distance. Okay, so that's why in the previous example I just put 1 for some distance, right? With respect to that only we'll be seeing the example. So this is how we'll be writing the expression for pheromone. Okay, this K won't come. Yeah. So but in that path, okay, in that path, lot of ants will be moving. Okay, we can't tell that only one ant is moving. Okay, we can see that n number of ants will be moving. Okay, so for example, in a path, if 5 ants are moving, the pheromone content will be the sum of the pheromone secreted by all the 5 ants. Right? In a path, if 5 ants are moving means the total pheromone content available in that path is a sum of the pheromone deposited by all the 5 ants. So we need to add it, right? So that's why in the path Ij, okay, K is equal to 1 to M. That is the number of ants. If 5 ants are flowing means 5. So add the pheromone content secreted by all the 5 ants. So that's the thing. Okay. In a path, the total amount of pheromone content means the total pheromone sum of the pheromones secreted by all the ants. If only one ant is going means that's one value. 2 ants are going means the sum of both. 3 ants are going means sum of all the 3. Like this only we will be calculating the total pheromone. Without evaporation, here we are not keeping any evaporation, just putting this. Okay. Now let me tell you. Okay. So this is a cost distance. Okay. As in that, I have 2 ants. So explaining by 2 is easy. Okay. I have 2 ants. Let me take the first ant. Okay. And I'll take one color for one ant. Okay. So assuming that the first ant is moving here, it's going to the destination, it's coming here, it's coming back. Okay, this is a path the ant is following. Okay, okay, that means it's going down, it's going up left side, then it's coming down. This is a path that ant is following. Okay, so L is a distance. Okay, 1 is for the first ant. The distance covered by first ant will be 5 plus 4 9, 9 plus 4 13 plus 1 14. Okay, here. Right, the first ant is taking this path. It's all assumptions only. Just for example, first ant is taking this path. So that is L1 is 5 plus 4, 9 plus 1, 10 plus 4, 14. So it is traveling a distance of 14. So tau of first ant is 1 by 14. Because we have seen, right? What is that? There's a pheromone is inversely proportional to distance. Okay, so the tau of the first ant is 1 by 14. Hope it is clear for the first ant. It is taking this path. So the distance is 14. Just count the numbers. That's all. And the tau, that is the pheromone deposited, is 1 by 40. Okay. Now let me come to the second ant. Okay, 1 second. Let me come to the second ant. Okay. And I'll just put it another color. Color and use yellow. Okay. So this ant is taking one second. Yeah, this is taking this path. Just take the yellow color. This path, this, and returning like this. Okay, so it's see, it can take any path. Just for example, I'm putting this one. It's going in this path. It is reaching the destination. Then it is going to this path. It's coming here and it's going back. Okay, I think the color is clear. It is taking this path. Okay, it can take any path. Okay, so only thing is that starting, go to the destination and return to the source. So if I take L2, go for another color. L. So this is L. L is for the second one. Okay, is you'll get 4 plus 8, 12 plus 4, 16 plus 15. It's 31. So path, that is the distance traveled by the second and will be 31. Okay, and tau 2. Okay, this color is very tough to see. Tau 2 is 1 by 31. Okay, hope this is the pheromone content we have calculated for both ants. The first ant is 1 by 14 and the second ant is 1 by 31. Okay, so these are the pheromone contents for the first 2 ants. Okay, so hope this is the first one. We have calculated the pheromone content for the first 2 ants. This is for the this equation. This equation we have done. Okay, this equation is done. Now let's calculate this one. Okay, that means in any path, the number of ants travel. If more number of ants are traveling, it is the sum of all those. If only one ant is traveling, it's the same. Okay. Right. So first one is this one. Hope you understood. Now let me go for the next one. When the total value. I have A, I have B, I have C, I have D. Assume this is the same as the diagram. Okay, so the first ant has traveled. This is a 1 by 14. This is 1 by 14. This is 1 by 14, and this is also 1 by 40. Okay. Yeah. So this is first and has traveled. Okay, and the second hand has traveled. If you understand, then this is very easy. Second hand has traveled in this one, so this is total is 1 by 31, right? Because two hands are traveling. Two hands are traveling means it's a sum. Okay, then it went to this path, so this is one this path. Okay, started with this path. This is 1 by 31. It came back in this path, so this is 1 by 31. It came back in this path. This is 1 by 31. So whatever path they are following, this number we have put. Okay, I'll just tell you the last one. You can see here. I just printed all those things. Yeah, you can see this. Okay, it first traveled. This is a blue color path. It's 1 by 14. Next one is a green color. It's 1 by 31. Okay, so in this path, both of them have traveled. In this path, both of them have traveled. Okay, in this path, only one person have traveled. So this is actually how we'll be calculating the pheromone content in each path. This is actually the mathematical expression. When you are putting this one in MATLAB, automatically it will calculate and give. So this is the second step. First one is to give the pheromone content. Second one is to add all those pheromone content in the path. Now we'll get an answer like this. Okay, this path is having 0.1. Okay, and this path is having 0.1, and this path is 0.07, like this. Okay, now by seeing the graph, you can understand, right? It's always, see this, if I starting from the source, I have this path and I have this path. But by seeing the graph, you can understand, obviously we'll take this path because the pheromone content is more here and this path is 0.7. So you can see the shortest path is this one. Simple, you can understand that. Okay, but let it be. I'll explain mathematically. Okay, this is the next step. Hope you can understand. First, I have deposited the pheromone. Now I have calculated the pheromone content. Okay. Now the next one is that practically when you are seeing the pheromone contents will evaporate. Okay, practically when you are seeing the pheromone contents will be evaporating. Okay, so that evaporation has to be converted into some mathematical equation. Okay, evaporation has to be converted into mathematical expression. See, these are all standard expressions. Here also another KK. Okay, these are all standard expressions. Okay, so this is the pheromone content it is going to deposit, and this is the pheromone contents earlier had. That means I have two iterations, iteration 1 and iteration 2. So in the first iteration, if I am having 5 pheromone, and second iteration means I am separating 2 plus the earlier one is 5. This is how it is going, right? First iteration I have some pheromone content. Second iteration, how much it is secreted plus what is previous available. Okay. So this is a hormone pheromone which is secreted in the first iteration, and this is the one which was there after the first iteration. Okay. So that is our first iteration, some pheromone content will be deposited. In the second iteration, some pheromone content will be deposited. Okay. And the sum will be what is available now and what is available previously. But the thing is that we need to introduce a factor which is called as evaporation. That means in the first iteration, nothing is there. When you come for the second iteration, some percentage of pheromone which is deposited in the first iteration will evaporate. Okay. That is practically happening. So that has to be converted into a mathematical formula. Okay. So this rho is a evaporation factor. Rho is a evaporation factor. So rho is the evaporation factor. Okay, so that will decide how much it is evaporating. Rho can take a value from 0 to 1. If rho is 0 here, what will happen is that it is understood that there is no evaporation. Okay, if rho is 0 means it's understood that there is no evaporation. So whatever it is deposited previously plus whatever it is deposited now, totally it will be available. But practically that is not happening. Okay, if rho is 1. Okay, and what happens if rho is 0 means, okay, then all path will have much pheromone content. So there won't be any much search in your problem. It will stuck within that value and it will end. Okay, if you am taking rho as 1, 1 minus 1 is 0, it is understood that whatever which is secreted in the previous iteration has evaporated. That's the maximum value which we give, 0 to 1. If I'm taking rho as 1, it is understood that whatever which is deposited in the previous iteration, it has evaporated. Okay. Now what will happen is that again it will secrete. This process will go. So what will happen is that it will take more time to converge. But there are a lot of search options are there. Okay, so 0 is the minimum and 1 is the maximum, but normally we used to take some value as 0.5. Okay, that 0.5 you'll be taking rho. That means half of the pheromone is evaporated. Okay, you can't take 0. If you take 0, it's understood that nothing is evaporated. If you're taking 1, it's understood that everything has evaporated. One will make your solution to stuck into a local value, but convergence is very fast. Another one will make search everywhere, but convergence will be very slow because everything is evaporated. So we need to take in between this. Normally we used to take 0.5. Okay, so the evaporation is 0.5. So this is a third step. Okay, like this. Okay, so assuming that I have first iteration and I have second iteration. Okay, so A, B, C, D. This is the path I have, and second iteration also A, B, C, and D. I have these many paths. Yeah. So second iteration we have seen, right? This is a 1, 1, 3, 3, 7, 7. Just for example, I am putting 0.1, 0.1, 0.03, 0.03, 0.07, 0.07. Okay. And the first iteration we don't know anything. We are giving full probability for all. So the pheromone deposit will be 1, 1, 1, 1, 1. Okay. So this is the first iteration. All pheromones are the same. But when it comes to the second iteration, the pheromone content will be changing. Okay. Now with evaporation, what will happen is that, okay, so I'm taking 0.5 as the evaporation factor, right? So you have the formula like this: 1 minus 0.5 into what was existing in the previous iteration plus how much is there in this iteration, right? 1 minus 0.5, that is 0.5, into how much was there in the previous iteration plus how much is secreted in this iteration. Okay, so previous iteration everything was 1, 1, 1, 1. In this iteration, this one. So how much remains is that 0.5 into 1 plus this one. Okay, so we'll be getting something around. Okay, so this is what we have. Yeah, this is a formula, right? So 1 minus rho, 1 minus 0.5 into what is in the previous iteration. So 1 minus rho is 0.5 into 1 that was existing initially into the sum, into this sum. Okay, so finally what we will get is that this is a probability. Okay, this is a pheromone, it's a pheromone content after evaporation. But after evaporation also you can see that this path is the shortest. Okay, so this is what we get after after evaporation. Okay, so this is how we need to work on this. Okay, clear? So this is the next step. First we have deposited pheromone. The second one is we have added everything and made how much is available in each path. Third one we have done with the addition, evaporation. Okay, now everything is okay. From this graph I can understand this is the shortest path, right? And this is another path, but the best one is A to B. Okay, yeah, but the thing is that how mathematically we will do is, because from seeing the graph I can understand this is the path, right? That means we'll be defining some probability. Okay, with that probability only it will choose that path. From this graph I can understand A to B is the shortest one, but mathematically we need to do it, right? So we'll define some probability which tells that, okay, this is the shortest path. If the probability is this much, you go through this path. If the probability is that much, go through this path. Okay, so now next one is to define the probability. Now I can understand this is the shortest path, but mathematically we need to define some probability. By that probability it will take this path. Okay, so the probability is defined. This is standard equation. Probability is defined as probability of taking this path ij is a tau available in that path plus eta is a length of the path, 1 by length. I'll tell you why it is added, divided by sum. Okay, that means what is a phenomena available in the path? This I'll tell you. What is this eta and sum of all these things. Okay, this alpha and beta, they are the control parameters. Okay, that means by changing the value of alpha and beta, we can control the working of this algorithm. Okay, that means generally if you see papers alpha and beta, they'll take from 1 to 10. So by changing the values, you can easily make our algorithm to converge. So that control is with alpha and beta. Okay, so that's the parameters alpha and beta. Generally the values from 1 to 10. So it depends upon the value of alpha and beta, the change will be there. Okay. Another one, why n is equal to, sorry, eta is 1 by Lj, why it is added means we need to give more importance to the shortest path. We need to give more importance to the shortest path. Okay. So 1 by distance, 1 by distance. Okay. So 1 by distance means if the, for example, I have two paths, one is having a distance of 5, another one is having a distance of 10. Okay. But I need to give priority to this path. No priority to this path. So it's 1 by 5 is 0.2, 1 by 10 is 0.1. So that is what I am multiplying with this eta. So shortest path will have more in the numerator. Longest path will have less in the numerator. That's just to give more the divergence to your problem. Okay. The thing is the longest path will have less value in the numerator and shortest path will have more value in the numerator. So more value in the numerator means more probability to choose that path. Then that path will be the shortest path. Less value in the numerator means less probability to choose that path. That is why this is added. Okay, but if you want, you can omit this also. You can see that in certain problems, in some papers you can see that they'll omit all eta and they'll just take only tau. It depends. If you want to run it nicely, you can add all those things. If most of the papers, in some papers you can see they'll omit eta and they'll just simply run with tau because there is a concept. Okay, either you can take eta or not. That depends. Okay. Yeah, so this is the equation by which you are calculating the probability. Okay, I have another 9 minutes left. Okay, so I'm just putting for each path how to calculate this one. Okay, so for the first path I'm calculating. That means what is the value of tau available into 1 by distance. Okay, so I'm just taking only 3 paths. Okay, one path, and one path, 3 paths, because calculating for 5 paths is tough. Just taking only 3 paths because from the source we have only 3 paths, right? Because from the source I have only 3 paths, so I need to start in any one of the paths. Then only I can go to another one, right? So I get to start calculating only for this path. Okay. So what is this available? 1. This is a 1 into 1 by distance. Okay. So that was the numerator, right? What is the eta? See, and for simplicity, the alpha beta is taken as 1. Else, again, it will be more complicated to explain. Okay. And most of the problems you can see, they'll take from 1 to 10. Okay. But for here, just for explaining simplicity, just to make it simple, I just taken as 1. So, what is the phenomenon available? This 1. Okay. This is 1. And the phenomenon available is this. So, it's 1 value. Okay. I'm sorry, this is the phenomenon, right? So this is one phenomenon into the second, and the sum is the same. That means this is the 4 is a distance and 1 is a phenomenon available. Okay, and 15 is the distance and 1 is the phenomenon. Just apply that formula. That's all. Just apply that formula. Okay, apply that formula. That's it. Okay, and I'm getting the value as 0.7595 for this first part. Okay, so first path I'm getting a probability of 0.7595. Just use that formula and calculate it. Okay. This is the distance and this is the phenomenon. Okay, and if I'm going for the second path, okay, so this is 1. Okay, 1 is a phenomenon I have and 1 by 15 is the distance. Okay, so like this I need to put. So if I calculate for all the 3 parts, the first path I am getting 75, second path I am getting 0.05, and third path I am getting 0.18. So if you see it in percentage, you can see that 76% chance is there to take this path, 5% chance is there to take this path, and 19% chance is there to take this path. Okay. This is how it's done. Or just you can see from the diagram itself, okay, you can see the distance here is 4, the distance here is 1, the distance here is 15. So normally when we see 1 is small, 15 is very large, 4 is in between. So obviously we'll choose 1 only, right? The same thing, the probability of choosing this path is 76%, the probability of choosing this path is 5%, and the probability of choosing this path is 19%. Okay, I'll wind up in another 5 minutes. Okay, some feedback is coming in. Okay, right. So now, see, we have seen only with respect to distance, right? Because all the pheromone contents are 1, 1, 1, 1, right? So now let's assume that somewhere pheromone content is more. Instead of 1, if this is 5, okay? Initially all are 1, with that 1 we calculated, but considering that somewhere 5 was there, okay? So we need to see that shortest path. So when you go for shortest path, first calculation we have done. But now the condition is that in some place more pheromone is there. That means more ants have moved through that path. So if I'm instead of 1, if I'm putting 5, I can see the values have changed. Okay. And now it's becoming 43, 3 and 54. Initially this path was the best one. 76% was there because everywhere the pheromone was same. But now this path pheromone was 5 when I was calculating. Now the chance of taking this path is very high. That means wherever you have more pheromone content, that path will be chosen automatically. That is the concept of this. Okay, wherever you have more, we can that path will be chosen automatically. Okay. Now this is also okay. Clear? So now this is done, right? Initially we have deposited pheromone, we have calculated the total value, okay? Then we have seen, then we have put evaporation in that. Then we have calculated the probability also. Now the probability is there. It's understood that one path is having more probability, right? Again, probability is a number, right? How to make the ant to go to that path? See, one path is having more probability. How to make the ant understand? You go to that path, go through that path. Okay. Now the next step will come. See, it's in a sequence. Now we have got the probability. Now we need to make the ant understand that their probability here is more. Take this path. Okay. So we have a lot of things to do that, but the most one is roulette wheel. Okay, so that is how. See, there are a lot of options to choose, but most of the things you can see they'll be using roulette wheel selection. Okay, the thing is that the first one, I think the first calculation you have seen, right? The first path has a 75 point some percentage, second path has 19, and third path has 5. This from here. 76, okay, 5 and 19. So this is done in toilet bill. Okay, 76, 99, 5. It is arranged. Okay, so 0.76, 0.19 plus 0.5, you will get 1. 0.19 plus 0.05, you will get 0.24. That's the wheel, right? And this is 0.05. So now we have a cumulative sum like this. Okay, so this is the probability we had. 0.75%. See, the probability we have understood that 76% is there. So this path is the shortest. Now we need to make the ant understand that this path is having the best probability. Go through this path. Okay. So again, the next process is coming. Now, see, in MATLAB, we need to write a code for this one, right? Just write a code to generate a random number. Okay, I'm going to generating a random number. Okay, I'm generating a random number from 0 to 1. Okay, so if the number is from 0.7 or okay 0.2, okay, this is the value, right? If the number is generated is from 0.24 to 1, okay, let me take this as the first path, okay, the second path and the third path. Okay, we have got 3 paths, right? Let me take this as the first path. Okay, the path 1 and 19 is path 2 and 5 as path 3. Okay, we'll just generate a random number in MATLAB. Okay, from 0 to 1. If the random number generated is from 0.24 to 1, okay, take the first path. If the random number generated is from 0.05, sorry, okay, yeah, it's 0.05 to 1 second. 0.05 to 0.24. This is the first path, second path, and third path. That means I have 1. So generate a random number between 0 and 1. If the random number is between 0.24 and 1, take the first path. If the number generated is between 0.05 and 0.24, then take the second path. If the number generated is between 0.05 and 0, take the third path. Now, depending upon the number generated, the path will be selected. But it's understood that you can see that it is from 0.24 to 1. So surely there is 76% chance, right? Because if I am generating a random number from 0 to 1, there is 76% chance to get this one. And there is some 19, that means 24 minus 5, 19. So 19% is there to get this number, and 5% is there to get this number. That's what we have, 76, 19, and 5. So if I'm generating a random number between 0 and 1, 76% chance is there to take the first path, 19% chance is there to take the second path, and 5% chance is there to take the third path. So first iteration is over. This is the second iteration. Now it will go on till the end. That means whenever you are taking an optimization function, you'll be having two things. One is that either you'll have a termination criteria with the more number of iterations or some convergence. Okay. So if it is reaching the more iterations, it will stop. Okay. So first iteration is done. Then you calculate the probability. Then go for the solutions again. Okay. So this is how ant colony optimization is carried out. Okay. So this is the explanation of equation for the ant colony. Now you can use this concept and you can go for your own application. Okay. And one thing, there are a lot of parameters in ACO. Okay. Information on heuristic factor alpha is there, beta is there, evaporation factor rho is there. One second, evaporation factor rho is there. Okay. And then pheromone strength Q and M, all such things are there. But alpha and beta, that you can decide 1 to 10. Okay, 1 to 10 is a value, but that depends on the problem. When you're running with different values, only we can see which one is better. But normally they'll give from 1 to 10. Okay, evaporation factor, we should not take a maximum value as 1, then fully evaporation. If you are taking less value 0, no evaporation, so you need to take in between. One will make your, I'll just tell you after this slide. Okay, and number of ants also matters. That means if you see the literatures, okay, you can find that in number of ants, if more number of ants is less number of ants are there, more chance for exploration is there. If more number of ants are there, more chance for exploitation is there. But that all depends on your application. Okay, so these are all the factors you need to tune for ACO. Okay, yeah, these are all just theory. Okay, I'll just tell you for rho. That is important. Okay, so this is a pheromone. Okay, that's an evaporation coefficient which represents the degree of pheromone evaporation. So if value is from 0 to 1, if it is very less, it's tough. If it is more, also it's tough. It should be in between these. Generally, we'll be taking 0.5. Okay, yeah. If it is too small, global search ability will be reduced, because too small means very less evaporation, same path will be taken again and again. If it is too large, everything will evaporate, it will try to find a lot of other parts. So convergence speed will be slower. So better to take 0.5. Okay, and now you may use it for your own application, because also working in power electronics, you can use it for power electronics application. See, for example, if I am taking this, right, economic load dispatch, we have all inputs like what are the ABC coefficients, what are the generations, all those things we need to take, we need to give as input, we need to generate the initial solution and we have to run it. That will take another 1 hour for explaining it. Okay, so that's all. Let me wind up here. It's already 3:32. Okay, so if you have any questions, okay, you can put it now, or else if you have some exam is going on, it seems. One more thing, let me tell you, if you have any doubt in this, or if you need any help in this one, feel free to put a message in my WhatsApp. Surely I'll help you out. Okay, now over to the coordinator.
Yeah, thank you, Dr. Sreejith, sir.
Yeah, thank you, ma'am.
For your wonderful lecture on ant optimization. It was easy to understand through your analogies. So thank you for your valuable time with us, sir.
Thank you, ma'am. Thank you very much. It's a happy to meet you all. If you have any clarification, you can feel free to put a message to me. I'll reply. Okay.
Yeah, thank you, sir. So we will go through the assessment for some 20 minutes and then we'll call you again for the valedictory function, sir.
Okay, ma'am. Thank you all. Then let me sign off.
Yeah, thank you.
Kalyani ma'am.